CLion, a cross-platform IDE for C and C++. Download now.
I'm Dominik. Welcome to my talk about optimizing data building in game development. And so this talk, I'm breaking up into roughly 3 sections. A bit of background about what data building is in the game industry, sort of the differences that you need to know about in respect to normal game code. And I'll go over briefly some concepts used in this presentation. Then there's a section for techniques. I'll just go over through a whole bunch of them that I've had to apply over the years. And then at the end, there'll be time for questions. Please keep, it's not that clear, but there's a slide number at the bottom left-hand corner. So please make a note of that and we can always go back to that particular slide. So a little bit about me. I've been programming since high school, like last millennium. And professionally since about 2005. I've worked in a whole bunch of fields, from embedded medical devices, defense software, stint in web development, and the last sort of like 12 years I've been in AAA game development. I did originally get into programming because of games, and I think talking to people here, a lot of people have had that same sort of situation. And just to make it clear, I guess I'm representing myself, not any employer, and the examples here I've just basically recreated based on knowledge that I've gained over the years. So a bit of background, like what is data building? It's often called compiling, converting, generating data. In game dev, it's often called cooking or baking, like we like our sort of kitchen terms. I personally like data building. It's because it's analogous to sort of building the code for the game. Its main sort of purpose is to pre-compute the data that's used in the game, so to optimize it, also to create additional data. So if you have like a level of geometry, you process that and you generate like collision or acoustics data, things like that. Also, you can kind of pre-compute a lot of stuff for rendering, so you end up having just prettier games as a result. So yeah, also optimizing and compressing the data is a big step. So a lot of the textures that you get nowadays in games, they're actually quite heavily compressed. And it actually takes a lot of time to do that in certain circumstances. And sort of not really done at the moment that much, but we generally still pack things into bigger files, but it's not as important as it used to be previously when you ran the game on spinning hard drives or optical media, where the actual seek time was very significant. So you wanted to organize the data in a way which you'd just be able to load sequentially instead of having to seek. But with SSDs and NVMe drives, its seek time is effectively 0, so it's not as big an issue these days. So there's a sort of spectrum, a range of possible designs for data build systems in games, going from the minimal, which is just load the files created directly from content creation tools into the game. So this includes, so you can directly load PNG, FBX or Maya files, or, plain JSON or XML into the game. It's more commonly done in sort of smaller games because there's not that much data. You don't need to do it that quickly. And at the other end of the extreme, there's games with like full optimization where they basically just load from disk into memory and patch a few pointers and that's it. But to get to that stage, you need to actually do a lot of heavy processing, using a lot of machines to sort of get to that situation. Usually the studios kind of end up having something in the middle where there's some processing, but not all the way. And of course, it depends on many factors, including the sort of the team budget, the scope, the size, the studio existing infrastructure. So if you already have like cloud infrastructure, you probably use that. Or if you have people that have developed their own custom build system, you might use that. Various things like that. In this talk, we'll be focusing more on the sort of AAA end of the scale, so sort of closer to the maximum. because that's where I've had most of my experience from. So some key differences between game code and data building code is that the game code, you end up being, it's very much frame centric. You have a concept of a frame, and you end up needing to sort of process everything within that frame, so you can minimize the frame time, and the other important thing is to minimize the lag and the jitter between frames. So you don't want a single frame to be really huge and then the rest of them to be really minimal. You sort of want very consistent frame times, because you sort of end up breaking the immersion for the player if you get like a frame every now and again that's like 100 milliseconds. You ideally want to keep frame times consistent and as low as possible. So that sort of means that any code which could take milliseconds, and I mean that literally milliseconds, such as loading stuff from disk, decompressing it, doing a web request, that all gets moved to background threads off to the side, so it doesn't interfere with the frame time. On the other hand, data building code, it's run outside the game, and it's run sort of before the game can even start. So the goal is always to minimize the amount of time it takes to build the game. So it's like a compile step. You want to minimize your compile time, so you want to do it as quickly as possible. So regarding that, the other thing that sort of game studios tend to do is reuse code between systems whenever possible. And this actually has some implications when you want to reuse game code to do this sort of data building stuff. The sort of main thing is to sort of the gotchas. The main gotcha is, well, I'm going through the gotchas. The first one is writing non-thread safe functions. What I mean by that is specifically sometimes in games you can write functions which that it'll only be run once in a frame. So you end up with making certain assumptions, like putting in static variables or thread locals, or just statics to cache a result, for example. So if you call that function multiple times in a frame, you sort of can reuse the value. However, when that gets run as part of a data build system, it can often be run in parallel, and you get wrong answers, wrong results. Related to that is writing systems as singletons. And, this is the classic example of why you don't want to necessarily hard code something as a singleton, because, sure, in the game, there might only be one instance. But if you want to do some parallel processing and have like 16 instances of these, so you can do things in isolation, it doesn't quite work out. The next sort of assumption, this is more sort of game-centric, is assuming that frame processing is actually happening. So one of the little sort of little things that you do in game development is you often have sort of arena allocators or frame buffers in terms of like little bits of memory where you can allocate, and the allocations only live for the current or 2 or 3 frames. So you can kind of allocate in these things, and they sort of get swapped out every 2-3 frames when they're no longer needed for these sort of bigger temporary allocations. When you do this in data building, though, no frames are actually being processed, or they shouldn't be. So you end up filling the buffer and crashing. Luckily, it's an easy situation to detect, because you'll get a crash pretty quickly. And then you can just sort of tweak something, relax something, and end up fixing that. The next sort of thing is related to that, which is assuming that game systems are initialized and running. So this goes that, it assumes that the rendering system is initialized and rendering to the screen, where you don't necessarily want to have a rendering window up and DirectX initialized, and because some of this processing may be happening on a server with no GPU at all. So you sort of want to create stubs for interfaces and things like that. And the next sort of thing is loading all the sort of data from things into like a shared system. This is usually good for a game, but when you're doing process, it makes sort of the data processing much harder to do because you put stuff in, or it automatically gets put in, and then you have to like be careful how you pull things out and serialize them to a file again. So the goal of doing all this optimization work is to basically minimize the amount of time it takes to process all the data, or at least verify that no processing needs to take place. So how do we do this? Well, the first step is only build things that have actually changed. Now, there's a few key points here. You need to keep a lot of dependency information, including the file names of things you process, the timestamps of those files, and also the hashes of those files. In this case, also the software version is a dependency itself, because in game development, like, you kind of iterate quite quickly. So the actual data structures that you use in the game will change quite rapidly. New data gets added, old data gets removed, things get changed around. So the software version, the output format, and the input formats are all dependencies that you need to manage. And in this case, the timestamp is just an optimization hint, because we actually want to rely on the content hash, not the timestamp, because that could be affected by, rolling stuff back in the version control, or moving things forward, or saving it differently. So hashes is king. The next thing is to use caches for everything possible. And there's sort of the two types of caches that you can use. There's what I call processing caches, which are used internally during data building. And these are things like that basically save on I/O and processing time. So you end up loading a bunch of, let's say, static world geometry and caching properties about that. So when different things require this geometry, they can just query the cache rather than doing all of that manual loading themselves. The other one is sort of what I call output caches, which is where you store your built data. So this is sort of a file system on a server, something that you can query. And, so instead of necessarily building something again, you can just fetch it from the cache. Now, depending on the size of the studio, this can be in, various different scales. So it can be local to the sort of studio, the premises that you're working on, to an office, to a team even, or to like a whole company level when it's shared across even different game teams. And the two big things about these sort of caches, especially the output cache, is that the content hashes are very important, and so is binary determinism. So to make sure that when you serialize the same data, it saves the binary of, the two files that save the exact same data is exactly the same. The next thing you can sort of do is you can actually cheat, because it is game development, and game developers do a lot of fake things and cheat and work away things. And that is to use stale data, because in a lot of cases, if an artist or a designer is working on something, let's say they're testing a quest or something like that, they don't really care that the nav mesh is exactly up to date. And the nav mesh is one of those things that can take a very long time to update. So they don't really care if it's up to date, as long as things roughly look right and they can test their, putting their little quest nodes and things in the world. And this also relates to different people care about different things. So like a lighting artist might not care about anything except the actual world meshes, not even care about collision. Whereas a quest artist or quest designer may care about collision and navigation, but not really about the lighting in the world. So yeah, cheating is acceptable. And the final point is try and process everything in parallel as you can, and that's sort of the crux of the matter. Yeah. So a little bit of a quick detour, some assumptions I've made for this talk. Some of the examples used later, I've built using sort of a custom job system with asynchronous I/O, and I ran them on like my old 4 or 5 year old PC, which is still fairly high spec, like 16, 32 cores, lots of RAM. But a lot of the stuff I'm talking about is for about processing data on a single machine. Now, this can actually be extended to multiple machines if you need. So just because it's on a single machine, you can use other bits of software to replicate and do different work across other machines. And the other thing is, well, this is mostly C++ 17 and 20, because that's where game development is at the moment, at least in AAA, because of not all the vendors support the absolute latest standards. The other thing is a bit of terminology. You get job, task. In this talk, I've tried to keep it consistent. So job means a small, indivisible bit of work. So effectively, like more of a function call, but something that you start and end. Whereas a task is a larger process which combines many jobs. Some can be run in parallel, like a parallel for or something like that, to do some sort of larger processing. I also use the term spin lock, which is common in game development, but maybe not so common elsewhere. And that's just like a mutex, but it just spins and it's a lot lighter weight. It's a lot smaller in the number of bytes that it uses. And flat map, which I think more people should be familiar with now than earlier, because it's an associative container where it just stores two arrays of keys and values. Well, there's other designs, but in general, it's a linear sorted container. So a quick bit, jobs run on worker threads. So you just have a thread pool that runs all the jobs. And in this particular job system that I've made, it's used a thing called a counter to be effectively the synchronization point between one or more jobs. So a job has a counter which needs to go down to 0 before it can get run. And after it runs, there's a second counter which it decrements when a job finishes. So you can kind of create this whole graph of, or theoretically a tree, or graph of jobs that for the processing. For reference, this is sort of similar to like the classic Naughty Dog job presentation from a while ago. And also recently, I think last year, a former colleague described it in the GDC presentation. And it's also briefly mentioned in the game engine architecture book, if people want to look that up. The other key thing in game development is, of course, a profiler. I've used Intel vTune here in my presentation, but some of the key thing is to have a profiler with instrumentation, because you want to instrument your jobs, your functions, just to see what's going on and to see all the timings. Sampling is not enough because sometimes the jobs are very, very short. So onto the techniques. The sort of first technique is, it can be considered kind of simple, but I just want to go through it. It's to keep, the principle is to keep the threads or in the thread pool doing useful work. Sort of the best way to make sure of this is to keep all of the jobs that you put on those threads roughly the same size. So it prevents, waiting for a single long job and then everything else is finished working, or it's a dependency, so you have to finish it and before you can continue. And jobs of roughly the same size, you're able to squish it and finish sooner. In that same vein, you need anything that's a long processing function, try and split it up into jobs. Sometimes you may get the case where different bits that are sequential might end up being able to be done in parallel. And then you can also use parallel algorithms to process like large arrays of data. The other sort of thing is to process different data types at the same time. So you don't need to like process all the meshes, then all the textures, then all the game data. interleave them, because often these things have different GPU, CPU, different hardware requirements. Some will be IO intensive, some will be processing intensive. And if you put them together, it's less likely to put a strain on any one system, and you'll actually finish faster because there's less contention. A key part of what I did was building a large world or large level. And the sort of key thing there is to try and pre-process as much data as possible into a cache. So then, even if you're processing it in parallel, everything can just read from that cache rather than doing its own loading for its own particular area. Of course, subdivide the world into regions and process each region. And in normal cases, you will end up with some regions taking quite a lot longer to finish than others because they have more content. You can kind of think it as like a bell curve almost in a 3D world. There's usually stuff, in terms of like a big city, it's usually in the center. But in terms of like let's say a medieval map or something, you will still have large sections where there's a lot more content than in others. So processing some of those areas will take a lot longer than others. The nice analogy is when you've got a jar and you fill it with the big rocks, and then you fill it with smaller rocks and then sand. So the goal is to sort of have some bigger jobs, but you have enough of the other stuff that it can process in parallel while the bigger ones are happening. Sometimes, though, you end up having to deal with exceptionally long tasks, and sort of think hours compared to minutes or minutes compared to seconds, something that takes an excruciatingly long time because of some reason. You sort of have to evaluate this on a case-by-case basis because it's no one fault. It could be a data issue. There's just designers have placed so many things into this one area that it's a degenerate case. Or it could be an algorithm issue, as in you have, bubble sorts somewhere, and normally it's like 2 or 3 elements, but it's like 500 in this case. Or it could actually be a code bug. One way I've dealt with a situation like this is to actually pay the cost of processing that area once. So you process it once, you build those things, and then in code or in whatever configuration you have access to, you disable that processing of that area for that resource type and make it only downloadable from the cache. Now, you might need to reprocess it occasionally, but it means that people aren't stuck processing something for 2, 3, 4 hours when they can just download it and get on their way, and they don't care about that area. The sort of next sort of thing brings up to like the caching of large worlds. So the big thing that you want is like a large world contains a lot of nodes. And so what you want to be able to do is from a specific, you want to query that cache for all of the things in that area of maybe certain types or just all the things. Sometimes you might only care for meshes or quest things or textures or collision data. So traditionally, you sort of use these sort of spatial partitioning algorithms like KD trees, oct trees, and even quad trees are useful because in a lot of games, even though it's a 3D world, it really is effectively a 2D map. So you can still get good value out of that. These do provide log-n access to things, but for querying larger areas, you might actually need to do that multiple times, and that can cost you. So one thing I did is I created this thing called the grid cache, and it's this alternative data structure for doing slightly faster 3D lookups. I basically created it when I needed to do the building for a large city. And I have seen similar things in related fields like in physics engines and stuff, but nothing exactly like this. You can kind of think of it as a sparse 3D array. So you can imagine like the map there of nodes. It's maybe not that clear. It was clear when I created it, but it's a flat plane with a big sort of square of nodes in the center. So it sort of mimics some sort of city-based map. So you start with all the nodes in the world, you load them. Then you, okay, that's not exactly visible, but there's grid lines there. So you partition the 3D space into a grid. So the grid size depends on how you want to query, or you know, you have to sort of guesstimate at some cases how you want to partition it. Then wherever there's content in one of those grid cells, you create a cell. And then all the non-empty ones you put into a map. And the key for the map is the effective 3D index of the cell. I'll get to calculating that in a few slides' time. So this sort of data structure allows you to compute the cell from a 3D coordinate and then figure out where it is and see if it's got any content, like if it exists. So it allows you to do kind of faster queries of what's in a 3D space. The choice of map comes sort of down to how you're going to access it, because you're paying an upfront cost to create it. So you end up with really how you're going to access it. Like if you're going to access it like a single area at a time and only that area, then you can use a hash map, because it's technically an O1 lookup for if it's correctly sized. And so yeah, if you do a query where most of the queries are exactly a cell size or smaller, that's the way to go. In my case, I ended up using a flat map, mainly because a lot of people were doing queries that were bigger than a cell. And because it's a flat map, at least in one axis, all of the cells are adjacent, like on the x-axis, so they're next to each other. So you can do fewer queries and you get a range at each sort of column of 3D cells.
To think about, like, since it's pre-computed, can you guarantee that question map is properly sized?
I always use the flat map, but you probably can, because you know the amount of cells before you insert them. So this is the way sort of you create the cell in the index from floating point x, y, and z from a vertex position. Effectively, it's doing some sort of packing with the cell counts on each axis. In a previous version, I actually had all of the number of cells in each axis the same, but you don't actually, that's not a strict requirement. You can just have a differently sized or different amount of cells in each direction. To do the other way, you sort of do this, where you modulo out the index at each stage. And sort of this allows you to have a fairly flexible way of creating an index from a 3D coordinate. Alternatively, you can just do the simpler thing, which is just bit packing. And this works if you have like 10, 16, or even up to 21 bits per effectively for the number of cells. So it actually ends up, you can store quite a large world in it. 21 bits, huge number of, was it almost 16 million on each axis. I think you'll be able to store it quite easily. So yeah. So the actual design of this is you have a top-level grid cache class, which is the sort of root object, and it has the sort of ways of getting queries. I use return value semantics because it actually works, and I use pointers in this case to provide easy access to the members of the grid node. You can also use indexes, so you can return a vector of uint32 if you want to optimize the memory a little bit, but I found that this is easier for other people to use. The one key point here is you also want to have a large item cell. So here, a specific out of the regular part of the world cell for large items. And that is because you will end up getting things, something like a light at the top of the world that has a bounding box that covers the entire map. Now, we create a grid cell for everywhere there's content, and that means everywhere there's a bounding box. So this would basically instantiate every single cell. So you have to pick a size that you want to have a maximum, and then anything above that you want to put into this catch-all. There shouldn't actually be that many. I think from memory it was maybe 100, 200 such things, and that was based on width, height, and depth being greater than 500 units. So there wasn't really that many things, but you do need it because then you just run out of memory creating grid cells. The next thing is the grid cell class itself. It basically stores two different arrays of grid nodes. I did this because you actually want to do two different queries for this data. There's a thing called owned nodes, and that's where the bounding box center of that node or that node's position is in that cell's dimensions. And there's also an array of intersecting nodes where it's just where that node's bounding box intersects. So the owned nodes is where you want to, if you want to distribute something into sectors or sections of a map, that's what you use, because otherwise you get things that should be in one sector being in multiple sectors, like if you're partitioning the map into different files. So that's where you use that one. And the intersecting nodes are useful when you're processing an area, like doing something like generating collision, and you gotta know every single mesh that intersects that area. So that's why you want to use that one. And of course, it's got the bounding box for just easy access. And finally, you have the grid node class, or struct, as it were. And this is the one where effectively it gets created one for sort of every node in the world. So you want it to be as tightly packed as possible, because there will be millions of them. For modern AAA games, we're reaching probably in the tens of millions and probably higher soon. So bitpack everything, do like, I guess if you're on Windows, which most game developers would be, you'd be using Pragma Pack to make sure that everything's next to each other. And the other thing is that you want to store indexes to other content, or pointers in this case, but you also want to store the things that you sort on, and that is important. So these actual structures are allocated in an external array, and I've used like a growable linear buffer where you can just allocate a section of them, fill them in, and then allocate more, and you never deallocate them for the lifetime of the program or lifetime of the cache. Simply because if we go back, we can kind of see we just refer to them by pointer. So we don't want to just have dangling references. So that's in that case. And notice there's one thing at the end, which is let's see if this works. Yep, the sort order. And that is a thing which effectively is an automatically incremented integer of the index of when this node was created. And that's just used in case you have duplicate nodes and you want to disambiguate and have a consistent sorting. So if everything else in it is the same, or everything else that matters is the same, you can use this field to determine an order. So this brings me to the next topic of actually sorting these things. So initially, my implementation was this, which is a nice C++ convenient way of doing it, quickest way of writing it. However, it very negatively affects performance in both compile time performance, as it has to be included in the header, and each file that includes it pays the cost of instantiating two templates and comparing them. And it also impacts runtime performance, especially in debug, because this ends up being a function call, and it prevents inline expansion or being expanded inline in the places where it's used. Sort of the easiest fix is to expand it out, just write all the code. However, this does fix the compile time issue because there's no templates involved. It's just very simple C++ code. But it still has the same issue as the std_tie version, where it prevents inlining of this function because it's just so massive. There's so many fields that you need to compare. So a sort of better fix is you split it into two functions, an inline function and then a non-inline function. And what you want is to put the important comparisons in the inline function. So in here, we've got the first comparison is the type of node. And that's generally important because you want to sort by you want to get all the mesh nodes commonly, or all of the text sort of collision nodes or things like that. So you want to have the whole array sorted by that property. And you got the path and you got the properties hash, and then you go into this non-inline function. And the hope is that you'll filter out almost all of them in the first three. And then you have that in a CPP file, and it ends up being that the previous function can get inlined, and then there's a simple call to this function. And at the end, there is that sort order, which is a tiebreaker in all cases because we sort of guarantee by construction that it will be different for every single node. So now that we've got the sorting, there's another thing is optimizing sorting of large arrays. And even if you do parallel sort, sorting of very large arrays can be expensive. And sort of the main reason is that you're paying an n log n complexity. The comparison function is evaluated n log n times, and memory is evaluated log n times. So the more bigger items you have, so if you're sorting big items or millions of items, it just uses a lot of CPU time. But we can do better. We can save a second or two, which might not sound like much, but if you're doing this hundreds, thousands, tens of thousands of times, like for every query of the cache, then it can add up. So this sort of shows the original sorting code for an example thing where you've got sort of a prefab, which is a collection of nodes, and you've got a node which has a few properties. And you got the sort function there that has a whole bunch of indirection, accessing different things through memory and comparing them. So it's a small example, but it still illustrates this point. So how do we optimize this? Well, what we do is we have a step that we execute in parallel to extract all of the values that we need to sort by and store them along with the index in another structure. We then sort that other structure, and then we have another parallel process to basically take the value, to move the values from the original to the result array, and then we swap the two arrays. So it also works for large items, as I've got there. So this is the code. It's, this is the sort of the node data structure for sorting, used for sorting. It's got the IDs extracted from the previous classes, and it's also got functions to fill and to compare. And then the optimized sorting code looks like this. We're actually technically, there's more code and it looks like it's doing more work, but it actually ends up being much faster. So in the lines 4 to 7, we fill out, yeah, this should be it. Yeah, so there's the first job where we fill the sorting data structure from the original data. We pay a cost there, but it can be done in parallel and it's completely independent. So all threads run without issue, without being contented. And then at the end, we do a parallel job and we fill in the result array by taking the sorted index and accessing that. So it's a read from a very large array and write into a very small part of the array. And that is a sort of a profiler capture of the job before optimization. And you can sort of see like, you got the parallel sort happening here and then the sort of merge happening here. And yeah, it's about, 2 and a bit seconds. So it's a small example, but it's still still important. This is what it looks like afterwards, and I've tried to keep the time scale the same. So you end up with the parallel job to create the sort array, and the parallel job to create the result array from the sorted indexes, and then the actual parallel path is much, much smaller. So you do pay extra costs, but you can save a significant portion of time. That's like half the time of the previous one. Yeah. And this is how it looks on a graph. My machine had 16 processor cores, 32 logical ones. So that may influence while it's sort of leveled out, or it could also be my job implementation. But you can see it's significantly faster no matter how many threads you use. And yeah. And yeah, so the next section is when building, to try and avoid blocking any threads. So basically with a job-based build system, you're running on a thread pool, and if any job uses some sort of mutex or blocking IO or spin lock, it can end up blocking that entire thread and no other job can run on it. And then, best case, you won't have any contention and it can run through and there's no issue. But the worst case is that this job is part of a job, will have to be run on many threads because there's many of things to process. So you end up effectively locking the entire machine. So all the worker threads end up getting blocked on some mutex or some read operation or something like that. So sometimes, unfortunately, locks are unavoidable because you will need to guarantee data safety. And so you need to lock and to do something. And sometimes locks appear in places you don't expect. Like I think from a previous talk, there was a lock in printf because it's got a lock to make sure that you only output to the console on one. Or at least it was when I wrote this. But yeah, so ideally you have no contention, but instead you just try and actually use the job system, the thing that you have, to try and synchronize access instead of using locks. So an example of this happening in real life was we had a system that was processing a lot of files. There was lots of shared data in it, so it loaded a whole bunch of stuff in, and then it needed to serialize individual files containing a subset of that big shared system. Initially, because we're game programmers, we use a spin lock to guarantee access on writing. And usually in a game, it's not a problem because you don't have many threads. You don't generally write anyway, except for like the save game, and then you have like a single thread writing it. So what happened is, what the hell happened? Okay. Yeah, so we had this sort of thing where we had a spin lock that guarded saving of the file, and we need to effectively serialize the file sequentially. The problem came when, I came into work and the processing took 100% CPU usage for many minutes. And normally when there's a long process, people don't generally grumble too much unless they can't do anything else. So if they can't watch YouTube, if they can't work on something else, that's when they actually grumble, and you get called in and say, hey, what's happening here? So as you know, came in the morning, got greeted by complaints. People couldn't multitask while building the data. So I ran a profiler and I came up with this. Of course, the brown is the CPU usage. And in this example, I've made the ordinary jobs, that sort of ordinary processing jobs, use 50% CPU so you can kind of see what's happening. And yeah, basically it, well, looked like it's doing some heavy processing. But what it's actually doing is it's just spinning, waiting for the lock to become available. And the more threads you have, the more likely something it is to spin. So first thing I did, change it to a mutex. Mutex is heavier than a spin lock, but it effectively, brings the time down to a minimum. So effectively confirmed that thing, and it basically showed that it was lock contention that was the issue. And in the profile, it looks like this. So now you can see the CPU is not actually doing anything, it's just waiting for a lock. So the way to fix this was to actually, sat down, thought about the problem, and realized, okay, well, we already have a way of dispatching jobs. And because of the way we've constructed our job system, we can actually use counters to form a graph. And so we can actually have more than one dependency chain of that influence jobs. So you can do all the processing, and then when you get the saving, you have another job, and that runs on a separate dependency chain. So it's got two inputs to it, one of finishing the processing and another of the last job that's saved, that was doing the save data. So when I changed to this, so the first thing I had to do was actually turn that big function of processing into jobs. So I could actually isolate the saving job into its own little segment. So I could then, instead of a lock, issue it on a separate job. So, and the result of that was the time taken was still the same, but because all the worker threads were not blocked running the different processes, you could actually do other useful work in between. So that was the extra code that I added. You still need a mutex to guard the counter from access from multiple threads. And then inside this little block, you add a dependency on the counter and then issue the job, and then the counter at the end of the job, which gets decremented, you save as the next data save counter. So you kind of end up creating this other linked list of all these saving jobs. There are other ways of doing this. Like, for example, you could also put things onto a separate explicit queue, like put it into like a vector or a deck or something like that, and have a thread in the background doing the saving, or periodically spawn a job to actually go through the entire array and save it. But this was just a way to use what we had and serialize it. So the result was we were able to actually do more work while this saving was happening. And it looked like this. And you can see, as you can see from the yellow on the right, all of the processing that used to take the whole amount of time now takes about half the time. And there's no real huge spikes of CPU usage or troughs waiting for some mutex or something to happen. So this is the sort of previous code. That's the, I would say, improved code, but it is more code. It's just more code to effectively do less work in a way. Yeah. So the next sort of step to optimize things is to parallelize system initialization. Usually this is kind of overlooked, but it impacts every time you start the tool. So in game systems, you end up having to load a lot of caches from disk, and hopefully they're serialized in some way, but you still, hundreds of megabytes, gigabytes of data that you load to prime your system so it's ready to process really quickly. So in this case, the big thing is to basically initialize the job system as soon as possible and then have everything done in parallel. And these days, like SSDs are really good at just, there's no seek times, so you can just load data from many different files and you don't even see that there's a penalty to doing that. Basically, that also means that you kind of hide the cost of all of these, loading all these different files. Because if you, for example, connect to a web service or a database on some other machine, that's usually going to take maybe 100, 200 milliseconds. And in that time, you can easily load a file, a few hundred meg file from disk and process it into a data structure. So that's the one. Another one is hiding cleanup costs. Now, okay, destructing objects does actually have a cost. And in this case, I'm not really talking about destructing a handful of objects. I'm talking about destructing hundreds of thousands or millions of objects. Now, ideally, these would be trivial, plain old data types where you can just allocate them in a piece of memory, in a so-called arena allocator. And then when you're done with it, you just dispose of it and there's no cleanup to be had. But in processing, oftentimes you get a situation where you need a string, a dynamic string or a dynamic vector of memory or something like that. So you can't always do things, or using RAII types. So the key thing to do in this case is to move that to like a dangling job off of the critical path. So you can still destroy millions of objects, which could take many seconds, but it's no longer affecting the processing of the next step, of the next thing. The way you can do this is, for example, in the code I worked on, the style was you create a context object, which would hold all the data that you need for processing. In that object, it was allocated to a shared pointer, like make shared, and then that shared pointer was copied into every single job lambda. So that kept the ownership, and then when the final job went away, it got cleaned up. Now, unfortunately, this meant that it was the final job of the processing, which other systems were dependent upon to be able to start their processing. So instead, the key thing was to create another dangling job with that shared pointer, so it would keep it alive, and other things that were dependent on the actual end of that sequence, processing sequence, could run, but your dangling thing could run at a later date. Now, some notes to remember: the resources aren't freed immediately, so it's not like true RAII, where you can, by exiting this scope, you're guaranteed to have it cleaned up. The scope exists far longer, and you end up with this other job that could be cleaning up things in the background. It also means that if that used a particularly large amount of memory, you might actually want to think about that and maybe not do that, or try and work a way around it. So you clean up that. So if you need that memory for something else, you clean it up specifically beforehand. And I guess the other thing is that because the cleanup is happening in parallel to other work, you have to be careful that your destructors don't actually use or interface with shared systems. And then the final one is to, let the OS handle some cleanup. Like, you don't necessarily need to deallocate all the memory, especially at the end of the program. There are some things you do actually need to clean up, but things like GPU and GPU resources you do need to explicitly clean up. And things that have at-exit hooks, like, for example, the vtune profiler, that ends up putting something in an exit. And if you quick exit instead, you don't actually get the full instrumentation saved correctly. So if you can do quick exit, do it. Otherwise, you end up with needing to do some sort of workaround. And one workaround I used is, because to run a profile, you need to specify command line parameters. You can actually add an extra command line parameter, which all it does is just waits at the end, just before quick exit, for like 10 minutes. And that gives you enough time to see that it's finished, like it prints a message and then waits, and hit stop in the actual vtune profiler or other profiler. And that will then collect all the stats, and you can just terminate the program, no worries. So, yeah. So in summary, process everything in parallel. That's, I guess, pretty self-evident to a lot of people, but it's good to refresh the simple things. Cache data when building worlds, like building large things, cache it. And then so things can just read individual bits and don't need to do custom loading. Optimize the sorting by minimizing the amount of data that needs to be passed through the CPU to compare and the number of comparisons that you do. Avoid blocking the threads. So if you have a specific job system, use that. Make sure that you end up not needing to block, not needing to have mutexes. Jobs kind of can form their own isolated units of work, and you can sequence them in specific ways so that you don't need mutexes or critical sections or things like that at all. Make startup and initialization parallel. That's just, it's a fixed cost at the start of every program, so it makes sense. And think about when and where to do cleanup. So at the end of the program, do you actually need to free all the memory, or you can let the OS handle it? Things like that. Anyway, that's the end. I think I'm under an hour, so there's plenty of time for questions.